Welcome everyone once more. For those who are arriving, we have plenty of seats, so just want to remind you, you can't stay on the stairs for safety purposes. So need to have you sit down somewhere. Okay, who has a cell phone? Can you raise your hand? Only you? Only this? No, come on. Tell me the truth. Who has a cell phone? Great. So I want you to get your cell phone, just like I'm going to do it, and we're going to turn it off. Don't put it in vibrate. The reason is, if you put it in vibrate, it's going to cause problems in the audio, and this is being recorded. So it would be nice if your cell phone doesn't participate in the talk. Yes. Thank you. Maybe you want to raise the volume a little on the back. Yeah? Can you raise the volume a little? More? Yeah? Better now? Yeah, okay. All right, yes. Say it again. The other side is dead? You're not hearing over there? Oh, I see. No sound on the right side from you. Is it better now? No, the left side is dead. I see. Can you speak?
Yes, hello? Can you hear that?
No? Okay, that's good. Let's check that. Let's get the speaker here to say something to see if that side is dead for the speaker too. Go ahead.
Hello? Can you hear this? Yeah. Oh.
Okay, so don't worry so much because he's the guy who's going to be talking. You don't care much about me. Don't worry. I'm going to speak a little louder, and hopefully you get it, okay? If you don't get what I'm saying, read. Emergency information, very important. This is earthquake land. I see some familiar faces. You've been to this auditorium before, but I have to tell you this again. In case of an earthquake, do not panic, do not worry. We're going to give you instructions on what to do. And the exits are down here, over there. There will be no lunch served today. And the only thing I want to remind you is that we should probably move that chair away from the door. Didn't like that. Okay. All right, let's get started. Another thing that is important to remember, August 26. It's an important date in your lives. Because there is an energy summer school at SLAC. Are you with me on that side? Energy summer school? You hearing? More or less. Let me try this. Can you hear me better? Yeah. All right. Okay. So much for technology. Energy summer school, August 26th, special public lecture. I don't know the speaker personally, but I heard it's very exciting. Has to do with lighting, efficiency. I don't know the details, but check it out on our website. It will be posted soon. Okay? It's a special lecture. Tonight, we have the pleasure, and I have the honor, to introduce this cool guy. He's called Stefan Funk. You can call him Funk. He was born in Berlin, and he studied in Heidelberg, the Max Planck Institute. He did his PhD over there. He liked it so much that he did a postdoc over there. And then he said, no, I'm going to go to California. All Germans come to California. They buy a convertible, So, without further ado, I think I'm going to let Stefan carry on from now. So let's walk.
Thank you, Eduardo, for this beautiful introduction. About the soccer, we have to talk, but that's fine. Before we do that, let's talk about the topic of tonight. So it's a great pleasure to have you all here. I'm very impressed by the number of you that turn out on this beautiful summer evening to hear about the marvels of the universe. So I will be talking about cosmic accelerators, engines of the extreme universe tonight. Okay, before I start, there are three things that I want you to take away from tonight's lecture. I will be talking about a century-old puzzle, which is the puzzle of the cosmic rays. I try to convey that we have developed new powerful instruments here at SLAC that might help to solve this century-old puzzle. And then in the end of my talk, you might be interested how all of this is relevant to you, and I will spend a few minutes to talk about how this is relevant to our future. The story of cosmic rays really is a nice detective story in science. It really highlights beautifully how ingenious people, through very intelligent experiments, find out about the universe we live in. So it's really a detective story, and it has all the ingredients to a detective story. It has some first evidence where people realize that something is going on that they can't really explain. Then over the course of the 100 years, they were able to build a case. At the same time, theorists helped us to come up with some suspects for this detective story. But the problem was, as we soon realized, that we were stuck with the tools we had at hand, and we needed help. And now we are getting the tools that we need to try to solve this 100-year-old puzzle. And at the end of my talk, I will describe all of this, and at the end of my talk, I will try to come to a verdict of this 100-year-old case. So let's start with the case. So the first hint was found by this gentleman, Charles T.R. Wilson, around the turn of the last century. He was a very careful experimenter, and he had a very nice tool at hand, which was an electroscope, something I brought here as well. So this is an electroscope. It's basically a very simple tool that consists of the following ingredients. It has a metal rod that is connected to the outside world and connected to the inside of this vacuumized, or can be vacuumized, compartment. And then on the inside, there are basically two metal plates that are connected with each other here and that are movable with respect to each other. And this is also what you see here. So what he did was he put electric charge, just like I'm going to do now, onto this. And what he realized was that the plates separated. So this wasn't terribly surprising if you think about it from your electrodynamics lecture in high school maybe, that if you put a positive charge to the top, the positive charge would just go along these two rods, and since both of these rods are positively charged, they will expel each other, because same charges just expel each other. So this part of the rod is positively charged, this part of the rod is positively charged. And this is what we see here. For those of you sitting in the front, you can see this, that the rods are separated. Okay, this at first wasn't really surprising, but what was very surprising to him was that when he let the electroscope sit, the rods came back together. This he couldn't really explain, because there was no way the charges could go anywhere. They couldn't go through the air because the air was insulating. There was nowhere they could go. So why should they get back together? They should stay apart as long as he would look at it. But they came back together. So this was a puzzle. And what it meant was that charges leak out. So he was surprised about that, and he did careful experiments. He went underground. The same thing happened. He went behind several centimeters of lead, which was known to be able to take out any radiation that might come from the ground or anything. Still, the rods came back together. So he realized that there must be some cause of radiation that actually generates electrons here that would basically neutralize these charges and bring the rods together. So there was some kind of radiation that he couldn't shield with lead, that he couldn't shield by going underground, that causes the charges to leak. The question was, where does this come from? So it was a puzzle for a while. Oh, by the way, he was awarded the Nobel Prize for this discovery because it was quite a nice discovery. Actually, you can do it too. You can build your own electroscope. It's very simple. You just need 5 ingredients that are shown here. 6 ingredients that are shown here. You can assemble them in this way, and you have your own electroscope with the 2 plates here that you can charge. If you can't, there's a nice description how to build this. If you can't remember that, just type cosmic extremes into Google, and it will take you to this PDF file, and there's a description how to do that. Okay, so Wilson realized that there was some source of radiation that caused the charges to leak. The question was, did this source of radiation sit in the Earth, or was it somewhere in space? So people had to come up with quite clever experiments to find that out. And one way was by Pater Wolf. He was a Jesuit priest in Paris. And in 1909, he took this electroscope up to the Eiffel Tower. You might wonder, why does he take it up to the Eiffel Tower? The reason is simple. To distinguish between radiation coming from the Earth or coming from space, he basically wanted to get away from Earth. So how could you get away from Earth at that time? Well, the highest thing there was at that time was the Eiffel Tower. So he climbed up the Eiffel Tower, he took his electroscope with him, and he tried to measure the radiation up the Eiffel Tower, and he wanted to see whether the amount of radiation increases when going up or decreases when going up. And that would tell him whether the radiation came from outer space or from the ground. If you read his notes, it was actually quite a tough experiment he did. He stayed for 4 days and 4 nights up the Eiffel Tower to do his measurements. It was raining and snowing, and there was no restaurant on the top of the Eiffel Tower at that time. So it was really a tough experiment. And what he observed was a slight drop in radiation. Now this was very inconclusive to him. He couldn't make any sense of it, because either he would have expected a large drop if the radiation came from the ground, or he would have expected a large increase if it came from above. Okay, so it was still inconclusive. But then in 1912, the Austrian physicist Victor Hess did the next thing that you can do when you try to get away from the Earth, which is you can go on a balloon. So he did a balloon flight. This is Victor Hess in 1912, shortly before, actually I don't know if it's shortly before or shortly after he landed, but this is him in his balloon with his assistants, and he did a flight from what is now Czech Republic to someplace in Germany. So you see the Germans, there you go. And what he established was that the radiation dramatically increases as he went up. So he went up to 5,300 meters with his balloon, at which time he had to stop the experiment because he became terribly sick. But, so he went up to that height and he measured the radiation, Strahlung, as it's said here in German, and he realized that the radiation really increases as he goes up. So that was the proof that there is radiation coming in from outer space. And he was awarded the Nobel Prize as well. So then people started to investigate this radiation, and there was some while where they did measurement and found out that this radiation actually consists of elementary particles. And then in 1937, this gentleman, Pierre Auger, found that these particles actually interact with the atmosphere. So the particle comes in, interacts with the atmosphere, and generates what is called a particle shower, which is just this one particle creates a bunch of secondary particles, as we call them, that make it to the ground. And these secondary particles is what Victor has measured with his balloon, or what was measured on the Eiffel Tower. And this is actually something we can measure also in this auditorium, and I encourage you to come down after the lecture, because here is what is called a cloud chamber, and you can see, if you view in the right angle, you can see the particles coming in. So secondary particles are all around you, are here in the auditorium. Actually, there's 1 to 2 of these secondary particles crossing your hand every second. Yeah? So your hand, 1, 2, 1, 2 every second. Okay, so this is just basically what you might be able to see in this cloud chamber. Okay, so now this detective story, the plot unfolds. So we have some extremely penetrating radiation coming from outer space. So we learned that they come from outer space. People later call them cosmic rays, where cosmic rays is actually a misnomer. They are not rays, they are particles. Cosmic rays are also very relevant for a place like SLAC, because subatomic particle physics really started with cosmic rays. Before we had accelerators, like the one here at SLAC, people had to use cosmic rays to study elementary particle physics. Actually, five elementary particles were discovered with cosmic rays, and the people that discovered these things were all awarded Nobel Prizes. Actually, and this is another example. This is one of the first accelerators that was built in Brookhaven. It's the so-called Cosmotron, which was built in 1950. And in the press release, when they started it, they said, the Cosmotron is a new machine that would accelerate protons to previously unheard of energies, comparable to those of cosmic rays entering the Earth's atmosphere. So when people first built accelerators, they basically wanted to generate something like the cosmic rays in the laboratory. Okay, so let's come to the case. So we know that cosmic rays come from outer space. The century-old mystery is, what is their origin? What object in outer space is responsible for the cosmic rays? Okay, so before we go there, let's talk about what we know now about cosmic rays. So what have we learned in the 100 years since they were discovered? We know what they are. We know they are mostly protons. 90% of the cosmic rays are protons. The hydrogen nuclei stripped of their electron. There are about 9% helium nuclei. And then there's a very small fraction, about 1%, is all the rest. So electrons, larger nuclei, and gamma rays. So really, cosmic rays are mostly protons. And if we talk about the sources of cosmic rays, so the objects that generate the cosmic rays, we really talk about the source of protons. The other thing we know is they arrive isotropically from all directions. So that means if we look in this direction, this direction, this direction, or this direction, we have the same amount of cosmic rays arriving at Earth from any direction we look at. Uniformly arrival direction. And the third thing we know, they have extreme energies. They travel nearly at the speed of light, and they really have extreme energies. And to better characterize this, I would like to show you this plot. which is the most famous plot if you talk about cosmic ray physics, and it contains a huge amount of different experiments that measured at different energies. So let me walk you through this plot. So on the x-axis, we have the energy of the particles. So I told you cosmic rays are subatomic particles, and they have some energy. Let's call this lowest energy 1. Then the highest energy that we see would be a gigantic number. Yeah? So they span a huge energy range. Okay, this is the first thing. Second thing is on the y-axis, we have the number of particles that are incident on Earth per area per time. Yeah? So up here, we have very many particles arriving per area and time, and down here we have very few particles per area and time. Actually, if you put the number 1 here, then this number here on the top of the axis would be this number. Yeah? So I think this is one of the most remarkable measurements that ever was done in science, to have something that spans this huge a range in both axes and shows a very simple correlation, which is there are many low energy ones. So low energies, there are very many. High energies, there are very few. Yeah? This is supposed to be symbolized by there are many fish in this, many small fish in the sea, and very few big ones. So if you want to put that in numbers, around here you have about 1 particle per square centimeter per second arriving on the top of the atmosphere. Yeah? So if your detector is 1 square centimeter, you have about 1 every second. In the middle, you have about 1 per square meter per year. So if you have a detector of 1 square meter, you have 1 particle in this detector per year. And down here, you have really very few. You have 1 particle per square kilometer per century. So if your detector is 1 square kilometer, you have to wait for a century before you find one of these particles. Okay? Also, they contain lots of energy. The total power of the cosmic rays to keep the amount of cosmic rays arriving at Earth constant in time is about the power of 100 million suns. The largest terrestrial particle accelerator that is soon going to start operation at CERN, the LHC, is somewhere here on this energy scale. So there's a large amount of energy that is only accessible through cosmic rays. And if you were to take 1 gram of these really highest energy particles, you could cover the world energy consumption for 1,000 years. Now, unfortunately, to select 1 gram, to collect 1 gram of these particles, we need a detector the size of the solar system. So I can't solve our energy problem with this, but there's a huge amount of energy in these particles. Okay, so cosmic accelerators can be compared to human accelerators the following way. Here at SLAC, we accelerate electrons to 45 and then a lot of zeros, electron volts. CERN will soon accelerate protons, not electrons, protons, to 14,000 and then a lot of zeros. Yeah? Nature's cosmic accelerators accelerates electrons or protons, probably both, up to a huge number times this many zeros. Yeah? So the point that I want to make is here on Earth we have some things that can accelerate electrons, some things that can accelerate protons. In the universe we have things that can accelerate electrons, that can accelerate protons. If we want to find the sources of the cosmic rays, which is the 100-year-old puzzle, we have to find the cosmic accelerators that accelerate the protons. It's very important. Okay, so if you talk to a physicist about the energies that are contained in the cosmic rays, it's absolutely clear that normal stars in the universe cannot generate the energy that is contained in cosmic rays. You really have to have extreme objects. They must be among the most extreme locations in the universe, and these sources take us to the limits of the laws of physics. Either they accelerate particles by completely new physics we have no idea of because we can't generate it here at Earth, or they use the physics we know here at Earth and are just accelerators on gigantic scales. But this we have to find out. When we want to investigate cosmic accelerators, we want to find the accelerators of the protons, and once we found them, we want to find out how do they actually do it. Do they do it the same way we do it here on Earth with electric fields, just over larger scales, or do they do it some other way that we have no idea of? There's no doubt that cosmic ray exists. We can actually even see it. So apart from this exhibit that I have here, we can really see it in what is called the aurora borealis, the northern light, which is caused by charged particles flowing into the atmosphere, interacting with the atmosphere, and creating fluorescence light in the atmosphere, just like in a fluorescence light bulb. So just looking at this, you have to believe that cosmic ray exists. They actually do affect us. They are thought to be at least partly responsible for the evolution through the alteration of genes. So if cosmic rays hit your gene, it might cause some mutation and might have an effect in evolution. As you can see here, we went from apes all the way to Brazilian football players or something like the pinnacle of mankind. It's important in carbon dating. Carbon dating is used to date something like, for example, the Shroud of Turin or something like that. Carbon-14 that is used has a half-life time of something like 5,700 years. So you might ask, why is there any carbon-14 left? Because it decays in 5,700 years. And the reason is cosmic rays, when coming in interaction with the atmosphere, generate carbon-14. The other thing is it is responsible for increased radiation on intercontinental flights. So if you do an intercontinental flight, you actually do the same thing as Victor Hess did back in 1912 with his balloon. You go higher in the atmosphere, so there's less atmosphere above you, and therefore there's more radiation up there. And also, cosmic rays might be responsible for computers to fail. So if a cosmic ray comes in, hits your computer chip, it might deposit some charge and might cause the computer to fail. There's an article that I read the other day that Intel now plans to tackle the cosmic ray threat, where they don't want to stop the sources of cosmic rays, but what they want to do is they have designed an on-chip cosmic ray detector to try to cope with the particle which originate in space before sporadically entering the Earth's atmosphere. So they have an effect on us, and they even made it to the mainstream media. These are the Fantastic Four, which in this story went on a space flight and were exposed to cosmic rays on the space flight, which turned them into Mr. Fantastic, the Invisible Girl, the Human Torch, and the Thing. I should stress, this is fiction. Just to make clear. Okay, so I told you about the cosmic rays and how much we learned over the past 100 years. Now the question is, why is it so difficult to determine the origin of cosmic rays? So there must be somewhere a source of cosmic rays in the universe, probably many sources of cosmic rays in the universe, and the cosmic rays make it to us. Why can't we just look and see where they come from? Well, the reason is that there are magnetic fields on the way from the source to us, and these magnetic fields cause the charged particles, the protons, to be deflected. So the protons basically, through the magnetic fields in the universe, lose their directionality on the way to, from the source to us. This is why they come uniformly from all directions. Yeah? So this is actually an effect that you probably know if you have an old-fashioned TV. There is exactly the same thing is used. There's a beam of electrons which is generated in the back of the television screen, and then there are two magnets which are used to deflect this electron beam. And the electron beam illuminates then the screen. And through the reflection of this electron beam, you can make a picture on the screen. Okay, so we need something that is not deflected by the magnetic fields to find the sources of cosmic rays. Okay, bear with me. Before I get there, I want to talk about the suspects. So our theoretical colleagues have also worked for the last 100 years to think about what could be the sources of cosmic rays, where could the cosmic rays coming from. And they came up with black holes, exploding stars, and expanding shock waves. Okay, so the idea is that you can have acceleration in the universe through waves. And this should not be terribly surprising to Californians, because you probably see it every day. If you go to the beach, you see acceleration in waves. Like these people are accelerated. In the universe, of course, you don't have water waves, but you have shock waves, giant shock waves that are caused by explosions in the universe. For example, on the right-hand side, there's just an image, 3 images of a time series of an explosion on Earth, and you see this shock wave appearing. In the universe, we have the same thing. We can have a star that collapses and explodes in a supernova explosion, and then we can have shock waves of material moving through interstellar space, moving outwards, and heating the interstellar material and thereby glowing, as we can see here beautifully in this animation, where when we look 1,000 years later after the explosion, we basically see this shock wave that moves radially outwards through interstellar space. One thing I should draw your attention to briefly if I show this movie again is not only do you see the shock wave, also you see this tiny little dot here, which is a neutron star that is also generated during the explosion, basically during the collapse of the star. And this will become important later. So keep that in mind, that giant explosions generate both shock waves and neutron stars. Okay, so we know there are shock waves within our galaxy. So just like in the animation I showed you before, if we look now, we can see these shock waves. For example, this is an image of SN 1006, which was observed in X-rays, in optical, and in radio. This is another image of a supernova remnant. This one actually has a quite famous story. It's called SN 1006 because it's related to the supernova explosion in 1006. Chinese astronomers made records of this explosion, so they saw the thing really explode, and they took notes. This is why we know that it happened in 1006. And it was so bright, it was probably the brightest thing ever observed by man that could write down something. It was so bright that you could read books or something similar they had at that time during the night for several months before it faded away. So this was really a giant explosion. There are also shock waves outside of our galaxy. This is a cartoon of what is called an active galactic nuclei on the left-hand side, where there's a giant black hole sitting here in the center. You have material on a disk falling into the center, and then you have a jet of particles coming out of the black hole. We don't exactly know how this happens, but we can observe it. And this jet of particles can also generate shock waves around this jet. And as I said, we see this happening if you look, for example, in this object, Na, which we can observe in X-rays or in radio, or this object. We really see these jets coming out. So we know that shock waves exist both within our galaxy and within in other galaxies, so outside of our galaxy. Okay. So now, how can we, so the theorists tell us shock waves can be used to accelerate particles. On the other hand, we know that there are cosmic rays that arrive on Earth, but we don't know where they come from. So a nice thing would be if we could connect the shock waves with the cosmic rays. So if we could say shock waves are responsible for generating cosmic rays. A problem, as I said before, cosmic rays don't point back to where they come from. They are deflected by magnetic fields in the universe. So are there particles that are not deflected? And the answer is yes, otherwise probably I wouldn't be here to talk about this. Photons, particles of light, are neutral particles that are not deflected on their way from the source to us. So we can really use these photons to search the sources of cosmic rays. Now photons come in many disguises, but the most obvious one is photons are visible light. So whenever you see something with your eyes, it's basically photons hitting your eyes. So this is a beautiful image taken not far from here in the Death Valley, where you see the stars at night, you see this broad band of the Milky Way. These are really, to see this, photons are hitting your eye. Yeah? I will, just to make sure why we see the Milky Way as a broad band of stars, I just want to make one comment. So you probably know we live in a galaxy that basically looks like this. This is a galaxy similar to ours, which has a large amount of stars in the center and then has these spiral arms, and we're sitting somewhere on the outskirts of such a spiral galaxy. The solar system is somewhere on the outskirts. Now, if we are sitting in this galaxy, so this is a view seen from above, but since we are in our galaxy, of course, we are really not viewing the galaxy face on, but we're viewing it edge on. And then, of course, the galaxy looks like something like this, so we're seeing it from the side, and therefore the Milky Way is a broad band and doesn't look like this. Yeah? So we can view the universe in optical photons, and it would look something like this. This shows the broad band of the Milky Way along this axis, and the center of the galaxy is somewhere here. So imagine this. So basically what we're doing here is take the universe, which is a three-dimensional sphere around us, and put it in a two-dimensional plot. Just like, for example, if we take the world and make a world map, we take a three-dimensional sphere and put it on a two-dimensional map. This is just the same. This is how we can view the universe. This is a picture of the whole universe seen in 2D. The center of the galaxy is here, the Milky Way is shown here, and this is if you exactly look in the opposite direction of the center of the Milky Way. Yeah? Okay. So, I said that we can use photons because they are not deflected by magnetic fields. However, photons of visible light are just a tiny fraction of all photons. Photons, in fact, basically cover about 1 octave. 1 octave is if you take the frequency at the low energy one, you take the frequency at the high energy one, just like on your piano, the frequency at the low energy one is half the frequency at the high energy end. Yeah? So basically visible light is about 1 octave. There's a low frequency end, which is somewhat reddish, which are low energy photons, and there's a high frequency end, bluish, which are high energy photons. Now if we take this image of 1 octave, then photons span something like a 15-meter long piano. Yeah? So the visible light is really just a tiny, tiny fraction of all the photons that arrive here. So you have to imagine a 50-meter long piano if you want to really access all the photons that arrive here on Earth. And you probably know about other photons. There are radio photons, there are infrared photons, visible light, what I just talked about. There are X-ray photons, there are gamma-ray photons. Now we can use, of course, photons in the visible light to view objects here on Earth. We can also use infrared cameras, for example, to image heat here on Earth. We can use X-rays to image things like bones in your body and things like that. And we can even use gamma rays here on Earth. For example, this is what is done in a PET scanner, where you can image parts of your brain, for example, using gamma rays. So if you want to use photons, you really shouldn't only use visible light. You should try to use the whole range of photons that are accessible to you. Okay, so on this, using these photons, it should be clear that gamma rays on this 50 meter piano have the lowest, the smallest, shortest, the highest frequencies, sorry, and therefore carry the most energy of all photons. So gamma rays are the highest energy photons we know of. And since cosmic accelerators, the accelerators of cosmic rays, are probably the highest energy objects in our universe, maybe we can use the gamma rays to observe the cosmic accelerators and learn something about the acceleration process, because we can't use the protons. Okay, gamma rays are really have a lot of energy. If you compare a gamma ray to a visible photon, it's actually like comparing $1 to the gross national product of this country. They are really, they have a lot of energy. Problem is, there's no free lunch. They are very rare. Just like the cosmic rays, when I said there are very many low energy ones and very few high energy ones, also in photons, there are very few high energy ones and very many low energy ones. So optical telescope, like the Hubble Space Telescope, collect zillions of optical photons within minutes. For gamma rays, we really have to fight hard, and we detect only a few hundreds of gamma rays per hour. They're very rare. On top of that, there's an additional problem with gamma rays, if we want to use gamma rays to observe cosmic rays, and that is gamma rays are absorbed by the atmosphere. So if you look at the different wave bands I talked about, radio, infrared, optical, ultraviolet, X-rays, gamma rays, the arrows here denote how far they make it into the atmosphere. And you see that radio make it to the ground level, so we can have radio telescope here on the ground. And then optical light makes it to the ground level, which is nice because otherwise it would be dark all the time outside. So optical light makes it to the ground, but gamma rays are absorbed in the atmosphere at a height of something like 25 kilometers. They don't make it to the ground. So if I put my gamma ray telescope here on the ground, nothing will happen. It's going to be dark. So this is why we have to place our telescope outside of the atmosphere. And this is how the Fermi Space Telescope that Eduardo mentioned before will come into play. Okay, so let's come back to the detective case that I outlined before. So we know cosmic rays arrive here on Earth. We know there are cosmic accelerators out there. We hope that they will shine in gamma rays. We know that the gamma rays point back to the source of cosmic rays because they are not deflected by a magnetic field. So we can try to investigate the properties of these cosmic accelerators using gamma rays. And the nice thing, and this is why it's so great at this point in time to be a gamma ray astronomer, is there are new gamma ray instruments that are really opening up a new window on the universe. Okay, so the idea is to use new instrument to find the origin of cosmic rays. And one of these new instruments is the Fermi Gamma-ray Space Telescope. It's a NASA project. This is why they have these beautiful images. It's following in the tradition of the what is called the 4 great NASA observatories, Hubble, Chandra, Spitzer, and Compton. And it is named after Enrico Fermi, who was the first person to suggest a mechanism for cosmic ray acceleration. Remember, gamma rays are rare, so basically Fermi is really the biggest thing you can lift into orbit without the space shuttle. It was actually launched on a Delta II heavy rocket. It's the biggest thing we could put into space without the use of the space shuttle. So how do we detect the gamma rays? Gamma rays are actually quite hard to capture, and we have to use state-of-the-art technology. What we use is a technique that we borrowed from our particle physics colleagues, and this is how SLAC got involved in this. The idea is the following. Our detector consists of many thin layers of material. And when the gamma ray comes in, it can convert into a particle-antiparticle pair in the detector. And this particle-antiparticle pair is what we can measure in the detector. So basically, it's really a particle, an elementary particle detector that we shot into space. So you can say SLAC now goes to space. Okay, here are some images of the detector here at SLAC before it was launched into space. If you look closely, you will recognize this famous Brazilian football player. There are even more of these people here, but still the detector you can see here in the back. This is shortly before it was installed in the rocket at Cape Canaveral. And then about a year ago, on June 11th, 2008 at lunchtime, the detector was launched from Cape Canaveral Air Station. It was launched into a circular orbit at an altitude of 565 kilometers, and it takes about 1.5 hours for the satellite to go around the Earth. And it's looking out in the universe, trying to detect gamma rays to find out something about the sources of cosmic rays. Okay, this is what it looked like after 20 seconds, which gave me the shock of my lifetime because I thought it was exploded. But then it made it up nicely, and this is the last picture I'm aware of, and after that we have to rely on the beautiful NASA imagery to see what happened then. So this is the liftoff. This is here the first stages are gone. This was the second stage. Now the fairing goes away. And then the solar panels unfolded. All of this worked nicely as we expected it. And since then, it's orbiting Earth. Every 1.5 hours, it's going around taking data. Okay, so now that I said all of this, we can look at the universe through gamma ray eyes. So instead of looking at the universe through optical, through photons, you can look at the universe through gamma ray eyes. And this is what it looks like. This is the first image of the universe as released by the Fermi team after 3 months of data. So it's a similar thing to what you saw before for the optical image. We see the band of emission, or I should say, yellow means a lot of gamma rays, blue means very few gamma rays. Yeah? So we see this broad band of gamma ray emission which coincides with our Milky Way. This is actually background to us, so we don't really worry too much about it. It's caused by cosmic rays hitting gas that is around between the stars in our Milky Way. So we knew about this before. But these individual dots that you see all over the place are really sources of gamma rays, and they are all cosmic accelerators. So they are really all extreme objects, and we are now in the process of studying them. So for example, these two are huge black holes with jets of particles and radiation pointing right at Earth. So you remember I showed you this picture of the black hole with the disk around and the jets coming out. These are these things. So for example, this one is a black hole which is 10 billion light years away, and overnight it became one of the brightest objects in the gamma ray sky. This one is actually my favorite object because it's the brightest gamma ray source in the sky. It's the Vela pulsar, and it's a rapidly spinning neutron star that has extreme magnetic and electric fields. Remember, neutron star is the little thing that was left over in the supernova explosion. This is exactly one of these, and it's the brightest gamma ray source in the sky. So why is it called a pulsar? It's called a pulsar because it's pulsing. Very good name. It was actually first detected in the radio, and when people detected it first in the late 1960s, they thought they had found extraterrestrial life because they got a signal which was perfectly periodic. So they thought some extraterrestrial life was sending a signal to us. Later it was realized that this was not the case, and I'll explain to you in a minute how we get these pulses. But this is a movie of the signal we get over time, and you really see how periodic it is. It fades away and then starts again in a really periodic fashion. Okay, pulsars are neutron stars. I showed you before they are leftovers from giant explosions, supernova explosion. Actually, I think pulsars, neutron stars, it's fair to say that they are really physics of the 22nd century. They are really exotic material in the universe. They have about 2 solar masses in an object that is the size of a city, 20 kilometers across. And if you take a sugar cube of the material of a neutron star, it basically weighs as much as all humans together. It's a really, really dense object. Because it's so dense, it has ultra-strong gravity, about 100 million times Earth. If you were to climb a 1 centimeter mountain on a neutron star, it's as much work as climbing the Mount Everest here on Earth. It has ultra-strong magnetic fields, about 1 trillion times the Earth's magnetic field. And it's spinning very, very fast. So it's rotating very, very fast around its own axis. And if you have a magnet that is spinning very fast around its own axis, it creates electric field, just like a dynamo. So it has ultra strong electric fields, about 1 million trillion times your power clock. So it's really, these are crazy objects. And what we think what happens is particles, so the blue lines here denote the magnetic field lines. So the neutron star is here in the center, and you have in blue the magnetic field lines. They basically look like the magnetic field lines around Earth, very similar. And because of these huge magnetic electric fields, you have particle acceleration basically along these field lines. So you have, just like in the case of the jet for these black holes, you have a stream of particles streaming outwards from the polar caps of the neutron star. And what is happening now, this thing is rotating fast, and every time this stream of particles hits you, you see it. It's basically like a giant lighthouse. So this animation is supposed to show it. So you have 2 streams of particles coming out at each end, and every time the particle stream hits you, you see a flash. This is how it's pulsing. Yeah? So now it hits you, now it doesn't. Now it hits you, now it doesn't. Now it hits you, now it doesn't. Yeah, and they spin very fast. So you see? Now it hits you. Now it hits you. Now it hits you. This is how it can be so periodic. Okay, so pulsars are really giant versions of SLAC in space. So SLAC is the accelerator is about 3 kilometers long. The electric fields we have in pulsars is a number that I can't say, but its size is about 1,500 kilometers. So it's about 500 times the size of SLAC. The energies we get out of it are about 2,000 times larger. The problem is, we know for a fact, they only deal with electrons. So it's really like a SLAC in space. SLAC only deals with electrons. These things only deals with electrons. So they don't really help us in the quest for the origin of cosmic rays. So where are the sources of cosmic rays? Now, to go back to this, there's another view on the Fermi sky that I have to show you. Now, this time, if you take the sphere of the universe, you basically just look from above and from below. So this is the northern hemisphere looking from above. I know you can't look at the universe from outside, but this is the sphere of the universe seen from above, and this is from below. And this is a movie showing what we see in the sky. Each frame is 1 day. And for the astronomers among you, I have just overlaid some of the well-known constellations on the sky, so you know which areas of the sky I'm talking about. The most important thing that you should note is that it's changing all the time. The Fermi sky is changing all the time. Actually, one of the nice things is if you look at this, this object that is moving down here, this is the sun. Yeah? It's moving over the sky because we're so close to the sun that it's moving with respect to all other objects. Then there are objects like this one, for example, or this one, that just rapidly change the output of gamma rays. Yeah? This is very bright and then just going away in a matter of days. So this is quite amazing for us. I briefly want to describe what we can learn from these very fast variation of the amount of gamma rays we see from these objects. Now, you should realize that light takes some time to travel. It takes about 8 minutes for the light from the sun to travel to us. It takes about 1 day for the light to travel to us from the edge of the solar system. It takes about 4.3 years from the closest star to travel to us. And it takes about 26,000 years from the center of our galaxy to travel to us. So, imagine that I would turn off all the stars of our galaxy at this very moment. What would it look like? Okay, so today, it looks like this. Now I switch it off. What does the universe look like tomorrow? Like this. Yeah. After 1 year, after 10 years, after 100 years, after 1,000 years, after 10,000 years. Yeah? So why I'm showing this is the following. If we see gamma rays changing the amount of gamma rays we receive from an object, if that changes on a matter of days, the object has to be very small. It basically has to be the size of our solar system. This is what we can learn from these very fast variation that we see in these objects. So this is quite exciting because what could these objects be? They are the size of the solar system, but they emit more energy in gamma rays than the sum of all stars of our entire galaxy. And the only thing that can do that are black holes. Yeah? So a lot of the objects that we see in the Fermi sky are black holes, and they are changing on very short time scales just because they are so compact. We're currently trying to work out whether these objects accelerate protons or electrons. We know they accelerate something because we see them in gamma rays, but we're in the middle of studying whether they accelerate protons or electrons. Okay, so let's come to the verdict of the case, of the century-old case of the origin of cosmic rays. Well, we can't tell now what the sources of cosmic rays are, but we're getting closer. We have, in the first 3 months of Fermi data alone, an enormous number of cosmic accelerators observed. And each of them is an extreme object that we have to study in detail to figure out whether they accelerate electrons or they accelerate protons. Pulsars, many of the sources we see are pulsars. They are the SLACs of the universe. They basically accelerate electrons. What we're searching for now are the CERNs of the universe, the LHCs that accelerate protons. And this is what we're currently doing. And this is very timely because hopefully before the 100th anniversary of Victor Hess's balloon flight in 1912, we can solve the puzzles of the cosmic rays. So let's come to the summary. I presented to you the century-old puzzle of the cosmic rays. I tried to show that we have now new powerful instruments that were developed at SLAC that might help us to solve the mystery and allow us to see how cosmic accelerators work. Now you might ask, where is this thing about how this affects us in the future? It really might matter in the long term. Cosmic rays are important in the long term for the following reasons. If we ever have to leave Earth, might happen, we have a serious problem with the cosmic rays. So I told you that the radiation level increases on transcontinental flights. So if you go high in the atmosphere, you get an increased amount of cosmic rays. In fact, people on the International Space Station, they report light flashes in their eyes, even if they have their eyes closed, which is caused by cosmic rays hitting their eye. And studies have shown that they have about a 10-fold radiation hazard up there. And remember, the International Space Station is still within the atmosphere. So if you go further out, the radiation hazard is much higher. In fact, there was a 1-week period between the return of the people from the Apollo 16 mission and the launch of the Apollo 17 mission. And during that 1 week, there was a giant solar flare, and the sun can also generate cosmic rays, lower energy cosmic rays. If the Apollo 16 crew had been out during that solar flare, and they just missed it by a week, if they had been out, they would have gotten a lethal dose within 72 hours. So this is really a hostile environment. It presents a huge risk for long-duration spaceflight and completely unsolved risk. And one thing is clear, once we are on the moon or on Mars, I think the first thing to do is to build deep underground bunkers to save us. But until then, let's try to find the origin of these things. And I stop here and ask for questions. And I encourage you to come down and look at the display afterwards. Thank you.
So let's thank Stefan again for this wonderful talk. We're going to have some time for questions, and I'm going to ask Stefan to repeat the question so that people in the back can hear. So let's start here on the front, Pierre.
Stefan, thank you very much for this wonderful talk. Why did our poor Jesuit get a negative result? Why did these results go lower as he went higher?
Yes, very good question. Okay, so the question was, why did the Jesuit priest Wolf get these puzzling results that when he went higher, the radiation didn't really increase? The reason is the following. The amount of radiation we have here on the ground is about, well, I'd say 2/3 is from radiation from the ground, and 1/3 is from cosmic rays. So he was just unlucky. He didn't go high enough. So what happened was the amount coming from the Earth decreased a little bit, and the amount coming from above increased a little bit, but he just picked the wrong height, basically.
I have a question in the middle there.
How does the black hole emit radiation? Because I thought, like, once light goes at the event horizon, it can't go back out.
Okay, so the question is, how does the black hole emit radiation? Well, this is a very good question. I don't have the answer to that, and I don't think anyone has the answer to that. What happens is, for some reason, the black hole generates this jet of particles streaming out. Yeah? So there's a disk of material going around the black hole, falling into the black hole. And once it's in there, there's no way out. But for some reason, the black holes, they have these jets coming out of the black hole. Jets of particles. Now, this might be material that never actually really made it into the black hole, but just evaded the black hole. In any case, if you believe me, and we observe these jets are just elementary particles, electrons and protons, and they radiate. These are processes that we know. The question is, how do these jets get generated? And the answer to that is unknown. This is a matter of current research.
Let me see on this side here now. Go ahead.
Is there any other way of observing the black holes or the supernova, the neutron stars, other than the cosmic rays? Any other way we observe them, or that's the only way we have?
Okay, so the question was, is there any other way of observing black holes and neutron star other than cosmic rays? Okay, I should clarify, the problem is we cannot use the cosmic rays to observe them, because on the way from the black holes and the neutron stars and whatever to us, they are deflected. We use the gamma rays. Yeah. So we can use all kinds of photons to observe them. We use radio waves to observe supernova remnants, for example. We use X-rays to observe supernova remnants. All of this we can do. But that's pretty much all we can use because we have to use neutral particles. I should add, if ever, we are currently building neutrino telescope, which is another kind of neutral particles that we could in principle use, but they are really hard to detect, and so far we haven't succeeded in detecting neutrinos from astrophysical sources.
We have a question in the very back there. Let me just ask the people if you can just hang in a little until we finish the Q&A session, because otherwise the people who want to ask the questions don't see the speaker. Thank you.
Are there gamma sources that Fermi has observed that we have no idea what they are?
Oh, yes. Very good question. So, are there gamma ray sources that Fermi has observed for which we have no idea what they are? The answer is definitely yes. It's actually very hard to unambiguously say what they are for each individual source. So there's, I would say, probably about 30–40% of the about 1,000 sources we have found so far. For those, we have no idea what they are. They could be something new, something exciting, we don't know.
Okay. I will go back to the center and then I come to the corner again. The back, please.
Yes, is there any way to measure the redshift on the gamma rays?
Very good. Okay, so is there any way to measure the redshift of the gamma rays?
Define redshift. Sorry, I couldn't help it.
Me or him?
You.
Okay, so redshift is as objects move away from us, as the universe expands, objects move away from us, and photons that are emitted from an object that is moving away from us are what is called redshifted. So their frequency is basically shifted. Okay, now with this, the answer, unfortunately, is no. I don't know of any way to measure the redshift of gamma rays.
We have a question on the very back there. I will come.
Oh, okay. So the question was, what kind of research got me the award? Okay, so the award was given, as they put it, these are not my words, for outstanding work of a junior scientist in the field of cosmic ray physics. So,
He doesn't know.
hold on. It was my work on cosmic ray physics. It was my work on gamma ray astronomy, on not on Fermi, but on a different instrument that we use to observe gamma rays from the universe.
We have another question here.
Huh.
How do we know that the gamma ray sources correlate at all? I mean, we know that the electron sources don't correlate with the photon sources. Why do we assume the gamma ray sources correlate with the photon sources? And the second one is, with these really high energy photons, why would we expect that they were so deflected? I mean, they're moving 300,000, almost the speed of light.
Okay, so the second question is, why do we expect these energetic protons to be deflected by magnetic fields? Because they move nearly at the speed of light. That was the second question, right? Okay, the answer to that is because they have a long way to go, basically. I mean, even if they are deflected by a tiny amount on a long, long way to go, they're still deflected by quite a lot. Yeah? The other question was, why do we expect a correlation between proton sources and gamma rays? Is that right? Okay. The answer is, well, okay. The simple answer is to generate cosmic rays, you need gigantic energies To generate gamma rays, you need gigantic energies. It would be very strange to have an object that can generate gamma rays and can't generate cosmic rays. Anything else? I can give you a better explanation, but that would involve a longer explanation.
And Stefan will be available for longer explanations. So let's take a few more questions. I see some same faces wanting to ask the same question, another question, but let's give a chance to other people. I want to go to the other end so that they don't feel ostracized. Somebody raised their hand there. You didn't, you lost your chance. Too bad for you. On the very back there.
Okay, how do you know the difference between a proton source and an electron source? This is an extremely good question. This is actually what we are doing every day, trying to fit together the pieces of all kinds of observations to see whether it fits better a proton or an electron source. We basically, what we need is to look at the broad band of photons from radio through X-rays to gamma rays. If we do that, there are clear differences between a proton source and an electron source. So basically what we need to do is we need to use Fermi to find the cosmic accelerators, and then we need to use all other wavebands to find whether they are proton or electron accelerators.
Let me translate it for you. When he says it's a good question, means I don't know. When he says it's extremely good question, I really don't know. Okay? But this question can be followed up if you come afterwards. He can give you more detailed explanation. It gets very hard. I think we're going to get close to the end, so I'm going to allow one more question. The gentleman here. Behind you, I'm sorry. You, yeah.
Gamma rays, okay, the question was, what about gamma rays deflected by gravity? Okay, in principle, this can happen, but it's not that likely. Okay, first of all, the deflection is not large. I mean, the deflection we know from optical photons or something like this is quite small. Like the deflection from some gravitational lenses. The angular resolution that we typically have with our gamma ray instrument is so much worse than the angular resolution for an optical instrument that we can't really see this deflection.
In other words, this was a really good question. So let's thank Stefan one more time for this brilliant lecture. And I want to remind you that there are some refreshments outside, and there will be people wearing red hats that you can ask them questions, and you can come back at the front to see the experiments and talk to Stefan. Thank you for coming one more time.